We're joined now by Dr. Gary Sims with our final presentation today on imaging applications in extreme environments. Dr. Sims has over 40 years of experience developing and testing solid-state imaging sensors and systems for scientific measurement applications, including analytical spectroscopy, astronomy, high-energy physics programs, bioluminescent measurement systems, and X-ray crystallography detectors. He is an author of numerous scientific publications and patents, and is president, CTO, and co-founder of Spectral Instruments. Dr. Sims earned degrees, Bachelor of Science in Chemistry from the University of Missouri, and Doctor of Philosophy in Analytical Chemistry from the University of Arizona. Welcome, Dr. Sims. We're very excited to have you today, and the floor is yours.
So yes, privately held company. We've been around about 30 years here in Tucson. We here in Tucson, we have Spectral Instruments and Spectral Instruments Imaging, which I'll explain in just a moment. And what do? We've been making mainly CCD-based imaging systems for scientific measurement applications. These would include things like the cameras used for the Catalina Sky Survey up on Mount Lemmon, and similarly for astronomical facilities all over the world. These are low noise, high sensitivity cameras, large area sensors, deeply cooled, and in some cases it involves a mosaic of sensors. So, as I said, astronomical imaging and spectroscopy. Some high energy physics applications, which will be part of our discussion today on extreme environments. Biochemistry and biological applications for things like microtiter plate reading, and live animal imaging, which is kind of an interesting topic in itself, but we'll just briefly touch on that. Certainly is not an extreme environment. We also developed over the years different sensors for different applications, a custom CCD or CMOS sensor when there's not a commercially available device that does the job. We also have expertise in packaging those sensors and cooling them to that moderate range of minus 20 degrees C to minus 120 degrees C. We also have maybe a unique capability in bonding fiber optics to those sensors when it's needed for things like an X-ray scintillator to conduct the output of a scintillator to that imaging sensor. And those are mainly used for X-ray imaging and X-ray diffraction applications. So here in Tucson, we have Spectral Instruments, the original company. And then now in Evanston, Illinois, Rayonics, they specialize in systems for X-ray crystallography. These are large molecule protein crystallography. And then a separate group here in Tucson, which focuses on the animal imaging applications. And lastly, a group in San Diego, headed up by Rob Billhorn, who's another U of A chemistry graduate, that focuses on electron microscopy, detectors for electron microscopy, and similar applications, both low and high energy electron direct detection. So here in Tucson, Spectral Instruments Imaging, imaging for laboratory mice. This is mainly used in pharmaceutical research and particularly in cancer research. This technique tells you where cells that you're interested are in the animal. And it's a good way to see that without having to dissect the animal. So the instrument does both luminescent, which is a challenging application, fluorescence, and there's also an X-ray system inside, so you can see where that luminescence is with in respect to the bone structure of the animal. In San Diego, direct electron, again, mostly electron microscopy. It's all targeted mainly towards large molecule three-dimensional structural analysis. Things like the COVID virus, what's its structure look like? It's also used some in material science applications, single atom and electron diffraction type applications. And that's especially in the electron diffraction, where we get into low energy electrons. In the material science and in the biological applications, there the energy is in the 100 to 300 keV electron range. And at those energies, the electrons really pass right through the silicon detector. And this is part of where we started to gain some expertise in detectors used in an extreme environments, because certainly when you're shooting your electrons right through the detector, that gets to be an extreme environment. Rayonics, again, focuses on large area detectors for X-ray crystallography. The camera hardware is normally built here in Tucson and goes up to Evanston to be calibrated and to have the computer system and software added to it. And then it goes out to one of probably about a dozen sites like this in the world. This is the ESRF, for the European Synchrotron facility just outside Grenoble. There are 3 or 4 sites like this in the US, Stanford, Brookhaven, Argonne, and then, like I said, about a dozen in the world. This is a synchrotron facility where the synchrotron's about a mile in circumference, and along there are beam lines where you get intense X-ray output. That is used to see the diffraction pattern from the molecule of interest. And those molecules tend to be large molecules, such as, again, using our current COVID problem as an example, the spike proteins that are on the outside of that. All the synchrotron groups were very busy getting the structure of those spike proteins as soon as the COVID became a recognized problem. So now we can transition into more of what the topic is today, and that is extreme environments. One of our customers that we've had for almost since the beginning of the company is the Lawrence Livermore National Laboratory in Livermore, California. One of their projects there that's been going on for all that time is the National Ignition Facility. And this is a project where they are really studying the basic physics of nuclear fusion, with the ultimate goal, of course, of being able to produce energy from it. This is something that's been going on since about 1950, and the physicists involved generally think, oh, this is not too difficult. We'll have this figured out in a few years. And now it's about 70 years later, they're still kind of about that stage. But have been making some significant progress in the last, I would say, 5 years on it. So this is really an experimental system, but it's a big experiment. You can see down here, there's a little tanker truck there. So you get from that, you get this idea of the scope of the facility. 192 laser beams that are fired all at once, and flash lamp lasers, and then they're doubled and tripled, and they all arrive in one small spot. And this is the target chamber. And the target chamber here, this is one of these legs is 4 of the 192 beams are in there. And you see there are some places here where it's not yet populated with laser beams. This was several years ago, before it was fully populated. Now that it is populated, you really can't get a picture of the target chamber anymore. Again, scope size of it, you see a fella down here. So ports for the 4 beams, and then these are for diagnostic instruments. And so those beams go in, they're focused down into this, what they call a hologram. Half the beams go in one side, half the beams the other side. Inside there is the target, which is just a couple of millimeters in diameter, holding some tritium and some deuterium. And when the beams hit it, all hell breaks loose. They get an intense burst of gamma radiation initially, followed soon after by a burst of 14 MeV neutrons. And that is early on in the development of this. The NIF project needed lots of cameras. And one of the ones they asked us to develop was this, what we call our 1000 series camera. It's a fairly compact for us, small camera, typically used for the Livermore project, a 4K by 4K CCD, moderately cooled. And it was typically fiber optic coupled into a street camera. And a street camera is sort of like a high-speed oscilloscope where the intensity of the light falling on it is of interest, unlike an oscilloscope where you just have really 2 axes. This is sort of a 3-axis device where it's X, Y, and intensity. So you need a precision camera to be able to measure accurately the light intensity. These are used in a lot of places. For example, making sure all those 192 beams arrive at the target at the same time. We've built a lot of other cameras that are used to actually observe what happens once the target explodes. But all of these are really kind of single shot types of things. You only push that button to fire the lasers once every few days. So once it's fired, you've got one shot to capture your data, and then you're done. So we built a lot of these cameras over the years. There's probably a couple of hundred or more there at the Livermore facility. And now the cameras are sort of a victim of the success of the NISP project, because now they're beginning to produce enough radiation in each shot that it will kill the cameras. Now, CCDs are not very radiation tolerant in general, and the rest of the electronics were never intended to be used in a high radiation environment. So now they've asked us to develop a 2nd generation, and it goes into the same instruments, the same streak systems that the earlier ones used. So it's the same physical size and shape and general format of the sensor, 4K by 4K, 10 micron pixels in this case, fiber optic bonded again. Now we've used a couple of different sensors here. One of them was developed by SRI under Jim Janicek, used for a solar orbiter. And there it has to be very radiation hard. So it's a very rad hard CMOS sensor. So we've used that, integrated that into this camera in one configuration. In another configuration, we've used the CMOS sensor developed by Direct Electron for their electron microscopy application. Again, very much radiation hard sensor. And we've done that in a back thinned version. So it's sensitive to, directly sensitive to low energy electrons. So both of these configurations of the 1600 camera, again, have to operate in this high neutron environment, 14 MeV neutrons at about 5 times 10 to the 9th neutrons per centimeter square in a very short burst. It's enough of a burst that it pretty much knocks any electronics silly. We cannot keep the camera operating through that. And the flash is so intense, there's really nothing to see anyway. So actually the camera is momentarily shut off. When the lasers are triggered, the camera is momentarily shut off, and then within 100 microseconds after the event, the camera is back on and ready to capture an image. That means that you don't actually see what happened when the target actually exploded. You're seeing something afterwards, unless you have a way to deal with that. And there's 2 ways to deal with that. And one is to capture that information on a phosphor that will continue to glow for milliseconds after the shot. So in the one version of the camera, we're actually looking at a phosphor that was excited during the shot. We're looking at the afterglow of it. In the other case, it's a little more interesting. It's using a process of what they call a time dilation. The neutrons strike a target, generate secondary electrons, and then what you do is let those electrons drift slowly down a tube. And so they arrive at the other end where the camera is, the camera that is electron sensitive, several hundred microseconds later. And by that time, all of your radiation has come and gone. So those are the 2 approaches used to actually capture the image data. And this is the 1600 the whole project is still in development. It's been going on for 4 years and it's still going on. We have now successfully captured images from what they call high yield shots. The shots that are producing, as I recall, about 5 times 10 to the 19th neutrons. And so things are looking pretty positive for the 1600. And now I'm going to put that aside because there's really very few people in the world who are interested in a camera like that. Not too many people have big lasers like that to shoot at things. But another project they asked us to do at the same time was this other little camera. And they just needed a monitor camera to keep an eye on various things that go on in this experiment during the shot. And when they use off-the-shelf cameras, they put them in there, they push the button, and a good number of the cameras would die every time they fired their lasers. So they wanted a monitor camera that could hold up to that radiation environment. And at the same time, we had been in conversation with other people who were interested in a camera that would run in a vacuum environment. Initially, it was 2 totally different things. So again, this little camera, all it needs to do is survive the shot. They weren't intending to even keep it on and running during the shot. Use a low-cost CMOS sensor. Wasn't intended for quantitative measurements. And of course, over time, those requirements kind of morph into something a little bit different. As soon as they found out it was also could be used in a vacuum, they said, oh, that's great. We'll qualify it for use inside the target chamber, and we'll put it inside the target chamber. Both those 1600 and this RVT100 cameras, the camera head itself is radiation hard. The rest of the we put as the minimum amount of electronics up near the sensor as we can get by with, just enough to get the digital data into a fiber optic and ship it somewhere else where it's a more benign environment. And this is the camera server box that accepts data from the camera head from a fiber optic cable, stores it locally, and then kicks it out over Ethernet connection to computer. So key thing is it's outside the radiation environment. We don't have to worry about all the design work for rad hardness. It is a gigabit Ethernet connection, so moderately fast, but not super fast. Now on the software end, there is either, you can run it through an HTTP server just from a web browser, or use something like GigiVision, which is an industry standard software to run it. So it looks a lot like a machine vision camera. One other thing we recently incorporated this is an intelligent power supply for the RVT100 inside this box. So the camera head for the RVT100 gets powered from this. When you run an RVT head in a vacuum, the heat dissipation is a concern. You really have to bolt it to something to get rid of the heat that it generates, and then you want to minimize the heat that it generates. And so what we've done with this is the power supply initially comes up with a higher voltage, and then it asks the camera head, what's the voltage at your end? And camera head tells us, and then it backs off the voltage until we have just the minimum needed to overcome the IR drop, which in these vacuum systems can be several hundred feet of cable, so a significant IR drop. So it backs off the voltage until just the minimum is needed to run the camera head and minimize the power dissipation. Again, the sensors are just off the shelf, more or less CMOS sensors. They are inherently radiation hard by the process. There is no special design for radiation hardness in the sensor, but using I think these were the 180 nanometer process, the thickness of the gate oxide is such that the parts are inherently radiation hard. 5 micron pixel, a 4K by 4K version, and a 2K by 1K version. You can get them with either color filters or monochrome. Most of the people that we're dealing with now prefer just a monochrome, because even though they weren't going to measure things with it, they end up doing it. They are available with 2 different thicknesses of silicon. The sensitive layer of silicon, either a 5 micron or 12. The 5 micron is what people would normally use for everyday use for the optical photons, so that the infrared photons just pass through and don't. The infrared photons will cause some crosstalk or some blurring in the image. So most people don't like that. They're using it for, again, optical imaging, but as it turns out, a lot of people we're dealing with want to look at something other than that, like soft X-rays. And for that, you like to have that thicker silicon. It makes it sensitive to X-rays of a longer energy. Even so, they're only really usable out to about 10 keV energy, 1 to 10 keV energy range. Well, actually, that's not quite true, because the 1 keV energy range is not the issue, because when you remove the micro lenses, which we can do with a plasma etch, then it's sensitive throughout the ultraviolet, throughout the soft X-ray range, all the way out to about 10 keV when the photons just start passing through that sensitive volume. And of course, like I said, this wasn't the original intent of the camera, but as soon as people start working with it and say, can it do this? And well, that's what it becomes. These sensors are not, and all these sensors are not immune to radiation damage. They are resistant to it. They do suffer from higher dark current over time as they're exposed to radiation. In this camera, it's a pretty simple thing to be able to replace the sensor in the field. Pull it out, push in a new one, go through a calibration procedure, and it's back up and going. So other uses for this camera, again, places where people need to look at things in a vacuum. We've got several being used now for the vacuum thermal testing of satellites. Both at NASA. There's one of the facilities on the East Coast initially, and then NASA Goddard, and then NASA down in Houston. Ball Aerospace, Northrop Grumman, all of these people who are building satellites, they stick them into a big vacuum chamber, and then they heat and cool the satellite or components of the satellite to mimic the space environment. And that camera has been found to be pretty useful for that. Again, using the fiber optic, we can easily go through the vacuum wall. We've got probably sold behind Livermore. This is probably the second most common use of these cameras at this time. So it is probably the only camera I know of its type that can really be run in a vacuum without modifications. Whenever you put it in a vacuum, then you've got other things to consider, like what lens do you use? The lens may or may not be suitable for use in a vacuum. You can make just a single, what you can't do is generally buy an off-the-shelf C-mount lens and screw it onto the front because it's going to have lubricants and such inside it that aren't compatible with the vacuum. The camera itself, again, it was tested at Livermore to ensure that it had a minimum of outgassing. So, we would say that it's suitable for use down in the 10 to the -6 torr vacuum range. Of course, you can go lower if you've got more pumping capacity. But it is not like an ultra high vacuum device. It cannot be heated above about 100 degrees C for bake out. So it does have its limitations. All right, one of the other applications is for, in the radiation world, is for looking at spent nuclear fuel rods. This is a company out of, I think, Toronto, Canada, that is using the camera for that. The fission nuclear plants generally store their spent fuel on site, and they want to look at them occasionally to make sure that nothing bad is happening to them, that the shell around them isn't breaking open. And so they need a camera that can withstand that. And again, there's just not a whole lot out there that'll do that. A couple of the other applications we've got going on for it are, again, at synchrotron facilities, up at Stanford for looking at the alignment of the beam, the electron beam in the synchrotron. And then we've got one up in Argonne at an intense X-ray source. It's an X-ray source where you basically take a bundle of X-rays, linear accelerate them to a high enough velocity. When they slam into the target, they generate not only X-rays, but a whole variety of energetic radiation that comes out that cannot be shielded. And they need cameras for a variety of monitoring mainly where did the electrons hit the target. And we just got an email from the guys up there this morning that, hey, the camera survived. They were very happy. So again, this type of camera is not suitable for use for everybody. Got a pretty limited market, but it's a rather unique product, a little niche market. But it's something that just wasn't out there, and a lot of people were trying to cobble things together themselves to make this work. So now, by virtue of having done this project for Livermore, we're able to give the scientific community another tool that they don't have to go out and make themselves. So that pretty much is the conclusion. And thank you for taking the time to sit here and listen to this, and open for questions.
Thank you, Gary. You certainly have put cameras in some challenging environments. I wonder if you could comment on what sort of the most extreme environment spectral instruments products have been in or are expected to be used in.
Well, some of the more, even on our astronomical cameras, at times we run into some pretty nasty environments. One example is a project that the Chinese government is trying to do and set up a telescope in Antarctica at a fairly high mountain plateau. It's about 10,000 foot elevation, where the ambient temperature is minus 80 degrees C, pretty much year round. So one nice thing is you don't have to cool the sensor. But you can only get there about once a year. They go overland and service everything, and in a 2-week period in the summer, and then they back out. So that's really much like a space mission. It's kind of like the Space Telescope. Even though it's on Earth, it's really hard to get to it. So things have to work reliably. And you only get a short window to service it, and everything is cold. Everything is minus 80. So things like cables and cable insulation, anything that's polymer, you have to really understand how it's going to behave at minus 80 degrees C. So that's just one example of an astronomical application. Of course, with astronomy, we traditionally don't get into space missions because those are usually carried out by larger organizations. Those are big projects. We have built cameras for sounding rockets, where you have the high shock, vibration, and acceleration considerations. But really, those aren't too bad. That's all fairly manageable. Radiation was a new endeavor for us. So we didn't have a background in that. We had to learn a lot about what had been done for space, which isn't directly applicable to the Livermore or the NIF program. We made trips, several trips up to Colorado to a testing facility there to test components and designs in gamma, X-ray, and neutron radiation environments. But there's really nothing that we can do to really mimic exactly what happens at the NIF facility. There's really nothing else quite like it. You can't duplicate it in a test environment. You have to stick it there at the facility and do the final testing there.
That is the test environment.
Yeah,
another question: what is the spectral wavelength range you have for testing capability in your Tucson facility?
Well, most of our testing is done with optical. We do also have X-ray, some X-ray sources. But most of ours is in the optical wavelengths. Not even currently, we don't have anything set up for ultraviolet. So visible wavelengths, and then some X-ray here. We have more X-ray facilities up in Evanston, because those detectors are all calibrated using soft X-rays from the 5 to 20 keV range. They've got a good facility for that. And then, of course, at Direct Electron, they have the facilities for the electron detection, both soft and hard X-rays, or electrons.
Okay, thank you. Another question: how deep a vacuum can the RVT-100 be used in?
Well, as I said earlier, it's really kind of targeted to that 10 to the -6 vacuum range. If you do go lower than that, there's going to be outgassing, and you really can't get around that, because you can't bake the camera above about 100 degrees C. So there will be water coming off, and but not much more than water. It did go through some rigorous testing at the NIF facility. They're very particular about what goes inside their target chamber. They can't afford to have things come off of equipment inside the chamber and deposit somewhere else where it isn't intended to go.
When did you have your first camera installed in the NIF?
Ooh, well, we had our that was interesting. We had the first camera for the first shot at NIF. In fact, I was out there, and the director of the project came by and looked at me and said, "That camera's going to work, isn't it?" I said, "Well, what can you say? Of course it's going to work." But it was the only camera that they had to collect data from that first shot. Just prior to the NIF, there was another project that was led up to it that was called NOVA. And so we initially had cameras on the NOVA project, but the NIF is a time when we really started building a lot of cameras for them. So yeah, it's from the beginning, and I don't remember off the top of my head what year that was, but it's.
Yeah, it's a very interesting facility. I had the privilege of touring it before they closed as well, the target chamber. So that was quite an amazing facility, and you guys are certainly doing some fantastic things there at Spectral Instruments, and really appreciate your time and the presentation.